A faint signal whispers across the universe, carrying the energy of billions of suns. Scientists call them fast radio bursts, or FRBs. Think of them as cosmic firecrackers, brief but brilliant flashes of radio waves traveling billions of light years. First discovered in 2007, these bursts last only milliseconds, but they've captivated astronomers ever since. Are they the dying cries of collapsing stars? Could they be evidence of intelligent life sending interstellar signals? Or perhaps they're the result of some colossal cosmic collisions that have only now revealed themselves? In the vast expanse of space, these enigmatic signals may hold clues to some of the universe's deepest mysteries. What if they could help us map the cosmic web or uncover the elusive missing matter that has puzzled scientists for decades? Strap in as we unravel the enigma of FRBs, a phenomenon so extraordinary it could reshape our understanding of the universe. Not all FRBs are created equal. Some are non-repeating, a one-time event akin to a cosmic sneeze. Others are repeating, sending out bursts at irregular intervals like a Morse code we can't yet decipher. This distinction matters because repeaters give scientists a rare chance to study their source in depth, potentially revealing their secrets. While their exact origins remain a mystery, theories abound. Could they be the result of massive star collisions, the wild magnetic fields of neutron stars, or even the gravitational chaos near black holes? The truth remains elusive, but one thing is certain: these bursts are more than just noise. They're a cosmic clue. Detecting FRBs is like listening for whispers in a crowded room. These signals are buried in the constant hum of cosmic radio waves, requiring advanced technology and a bit of luck to find. Thankfully, scientists have built some incredible tools to catch them in action. Take CHIME, Canadian Hydrogen Intensity Mapping Experiment, for instance. This telescope isn't your traditional towering structure. Instead, it's a series of stationary curved antennas in British Columbia, scanning the sky like a giant cosmic radar. CHIME excels at catching FRBs because it monitors the entire northern sky daily. It's like having a 24/7 surveillance camera for radio waves. Then there's ASKAP, Australian Square Kilometre Array Pathfinder, which adds precision to the hunt. ASKAP can pinpoint the location of an FRB's origin with stunning accuracy. When these telescopes work together, it's like having a magnifying glass and a GPS for the universe. The process doesn't end with detection. Advanced computational tools sift through mountains of data to identify these fleeting bursts. It's a race against time. Each FRB lasts just milliseconds, so scientists need to act fast. Despite the challenges, these tools are uncovering more FRBs than ever, giving us glimpses into their mysterious nature. Repeating FRBs are the holy grail for astronomers. Unlike their one-time cousins, these bursts offer multiple chances to study their behavior, making them easier to trace back to their origins. Imagine getting a second, and sometimes third, chance to watch a celestial fireworks show. That's the appeal of repeaters. Recent breakthroughs have identified 25 new repeating FRBs, adding to the growing catalog of known sources. This isn't just an achievement in numbers, it's a step closer to understanding these enigmatic signals. For example, one famous repeater, FRB 121102, was traced to a galaxy 3 billion light-years away, nestled near a star-forming region. Its repeated bursts allowed scientists to study the conditions of its origin, offering clues about what might cause such powerful signals. Repeaters are also excellent cosmic cartographers. As their signals travel through space, they pass through intergalactic gas, leaving an imprint that scientists can study. These imprints help map the invisible parts of the universe, like the distribution of matter in the vast cosmic voids. In many ways, repeating FRBs aren't just a phenomenon to observe, they're tools that help us explore the uncharted territories of space. The cause of fast radio bursts is one of astronomy's most tantalizing mysteries. Scientists are armed with theories, but no definitive answers yet. The leading explanation points to magnetars, a type of neutron star with intense magnetic fields. When these magnetic fields twist or crack, they could release colossal amounts of energy in the form of FRBs. Another plausible theory involves colliding neutron stars, the remnants of massive stars after a supernova explosion. When two of these stellar remnants merge, the resulting energy release could create an FRB. Such collisions often leave behind black holes, adding an extra layer of intrigue. But not all theories are so conventional. Some scientists hypothesize that FRBs might be related to black hole activity, such as the material swirling in their accretion disks. There's even the possibility that these bursts are signals from advanced alien civilizations, a hypothesis many remain cautious about but cannot completely dismiss. Interestingly, FRBs could also emerge from gravitational interactions, such as the tearing apart of stars by supermassive black holes. The diversity of FRBs, with some being single bursts and others repeating, hints that there may not be a single cause. Instead, FRBs might be a category of phenomena produced by different cosmic events. Fast radio bursts aren't just fascinating, they're valuable tools for understanding the universe. One of their most significant contributions lies in uncovering the missing matter of the cosmos. While most of the universe's matter has been accounted for, a portion, scattered as diffuse gas in intergalactic space, remains elusive. FRBs, traveling across billions of light years, interact with this gas, providing a way to study its properties. FRBs also help scientists map the large-scale structure of the universe. Their signals, distorted by the matter they pass through, act as tracers of the cosmic web, the vast network of galaxies and voids that make up the universe. This insight is crucial for understanding how the universe evolved over billions of years. Moreover, studying FRBs could shed light on exotic physics, such as the behavior of matter in extreme environments. Magnetars, black holes, and neutron stars, all potential sources of FRBs, operate under conditions that challenge our understanding of physics. Finally, FRBs could one day become tools for practical space exploration. Some scientists speculate that studying these signals might help refine our understanding of space-time, potentially aiding in future navigation across interstellar distances. The journey of FRB research has been marked by groundbreaking discoveries. The first detection in 2007 was a game-changer, proving that these phenomena exist. This detection, known as the Lorimer burst, was so unexpected that scientists initially questioned its authenticity, suspecting interference or equipment errors. Yet, it paved the way for a field of study that's still expanding. A major milestone came with the discovery of FRB 121102, the first known repeating FRB. This repeater allowed scientists to trace its origin to a galaxy billions of light years away. The data revealed that it resided in an active star-forming region, suggesting that young magnetars might be involved. Another leap forward occurred with the advent of advanced telescopes like CHIME and ASKAP. These tools dramatically increased the detection rate of FRBs, revealing dozens of new events, including more repeaters. In 2020, scientists even observed an FRB from within our own galaxy, tied to a known magnetar, providing the strongest evidence yet for their connection. Each discovery brings us closer to understanding these enigmatic signals, turning what was once a cosmic oddity into a key to unlocking the universe's secrets. Despite the progress, FRB research is fraught with challenges. For starters, FRBs are incredibly brief, lasting only milliseconds. This makes their detection and study a race against time, requiring ultra-sensitive instruments and sophisticated algorithms to catch them in real time. Pinpointing their origins is another hurdle. Many FRBs come from billions of light years away, making it difficult to determine their exact source. While telescopes like ASKAP have made strides in localization, it's still like trying to find a needle in a cosmic haystack. Moreover, the diversity of FRBs, some being single bursts, others repeating, complicates efforts to find a unifying explanation. Each new discovery raises more questions. Why do some FRBs repeat while others don't? Are they caused by different phenomena? Another challenge lies in interpreting the data. FRB signals are distorted as they travel through space, affected by intergalactic matter, magnetic fields, and gravitational effects. While this provides valuable information, it also makes the analysis more complex. Finally, funding and resources are always a limitation. FRB research requires cutting-edge technology, and competition for telescope time is fierce. Despite these challenges, the field continues to grow, driven by the promise of unraveling one of the universe's greatest mysteries. The future of FRB research is as exciting as the phenomena themselves. With the rapid advancement of telescope technology, astronomers are poised to uncover even more secrets about these mysterious bursts. Facilities like the Square Kilometer Array, SKA, set to become operational in the coming years, will offer unprecedented sensitivity and resolution. SKA is expected to detect thousands of FRBs annually, providing a treasure trove of data for researchers. In addition to better detection, future studies aim to answer lingering questions about their origins. Are all FRBs caused by the same phenomena, or are we dealing with multiple mechanisms? The increasing detection of repeaters alongside single bursts suggests that the answer may not be simple. Another promising avenue is the use of FRBs as cosmic tools. Their interactions with intergalactic matter can help map the large-scale structure of the universe with unparalleled precision. This could lead to breakthroughs in our understanding of dark matter and dark energy, two of the most enigmatic components of the cosmos. Collaboration will also play a crucial role. Global networks of observatories combined with artificial intelligence will make real-time FRB detection and analysis more efficient. As the field grows, FRBs might transition from being cosmic curiosities to essential tools for exploring the universe's most profound questions. Fast radio bursts represent one of the most compelling mysteries in modern astronomy. In just over a decade, they've transformed from a puzzling anomaly into a vibrant field of study, drawing researchers and enthusiasts alike into their enigmatic world. These millisecond-long flashes of radio waves hold the promise of revealing the universe's hidden structures, answering fundamental questions about its origins, and possibly pointing to phenomena we haven't yet imagined. But their allure goes beyond pure science. FRBs ignite the imagination, fueling speculations about alien civilizations, cosmic collisions, and the boundaries of physics itself. They remind us of how much we still don't know, serving as a humbling testament to the vastness of the universe. As telescopes grow more powerful and our understanding deepens, the day may come when FRBs are no longer a mystery, but a key to unlocking the secrets of the cosmos. Until then, they remain a captivating enigma, urging us to look up, ask questions, and push the boundaries of what we know. In their fleeting bursts, FRBs echo a fundamental truth about humanity's relationship with the stars. The universe is vast, and its mysteries are far from over.